Hey, welcome back to your favorite intermediate algebra class. We're going to talk about some linear programming today, and that's our objective is to solve some linear programming problems. Okay, linear program is the process of optimizing a linear objective function subject to a system of linear inequalities, which are called constraints. So what's going to happen is, let's look at this first example here, and I'll come back to that slide there. You have this objective function, okay, given that we're trying to find the min or max of, and then it's subject to these constraints. Okay, so we're going to look at that graph there. The constraints are those linear inequalities. The objective function is just that linear function that's optimized. Okay, and so what you're going to have is once you graph those linear inequalities, you're going to have this feasible region, which is just the graph. Okay, like here's the feasible region on that one, that shaded portion there. Including those solid lines as well. So the graph, the solution of the constraints there, that's your feasible region. Um, and then the optimizing this is just the process which you find the max or min. Well, the optimal solution of a linear programming problem. Okay, so let's look at this first little paragraph here. If an objective function has a max or min, it must occur at a vertex. Okay, so if it's bounded, see this bounded region, okay, it's going to happen, okay, if it's bounded, you're going to have both a max and a min. And so you got to check each of those vertex points right there, each of those vertices. That's where it's going to occur. Now, if it's unbounded, like over here, okay, if you have a max or min, so if you have a max or min, it will occur at a vertex. Okay, but again, it doesn't always have a max or min, so you got to be real careful with an unbounded region. Okay, so let's look at this first one here. Find the maximum of this objective function there, subject to the following constraints. So we go ahead and we graph each of these first to find our feasible region. So x is less than or equal to 2. So we graph x equals 2 as a solid line, less than or equal to. So we go ahead, test a point, and we say, oh yeah, it's over here. We won't go into great depth again on this. Y is greater than or equal to -1. So solid line y equals -1. We test a point greater than or equal to -1. Okay, so far so good. And then this third one here, y minus x is less than or equal to 3, or y is less than or equal to x plus 3. So y equals mx plus b. Our y-intercept is 3. And we're going to go up 1 over 1, up 1 over 1, up 1 over 1, and so on. Okay. All right. That's down. Okay. So, and then y is less than or equal to, I test a point again, and it ends up being below. Okay, so you can see our feasible region here is right in here. That's where they're all shaded, aren't they? That's the solution to that system of inequalities there. So, okay, so we see our constraints. Now, what we're looking for is our vertices here. Okay, so we have vertex, this vertex, and this vertex, okay? So we need to test each of those points. So -4, -1, that's this first one right here. -4, -1, I got to test that one in our objective function, okay, that top function. And then I'm going to test, looks like that's 2 comma, what is that, 2, 5 right there. I got to test 2, 5, because again, the max or min is going to occur at one of these vertices. And then the other one is that 2, -1 right here. 2, -1. I'm going to test each of these. And you notice that this is a bounded region, so I'm going to have both a max and a min guaranteed. Okay, so I say, well, my objective function, c equals 2y plus 3x, I believe it was. Let me check that. Yep. Let me test that vertex first and see what I get. So I just plug in x and y. Looks like I get negative 2 minus 12, so negative 14. Okay, that's what that c is equal to. That's the value, negative 14. Now I'm going to test that 2, 5 into 16, and then 2, negative 1. 2 times y plus 3 times x. So negative 2 plus 6, looks like we got 4 here. Okay, so well, it looks like our maximum here is right there, 16. That's our max value for that objective function, isn't it? It's bigger than that negative 14 or that 4, and it occurs at 2, 5. So our max c equals 16, and it occurs at 2, 5. Okay. Our minimum c value here for this objective function looks like it's going to be right here, that negative 14. So c equals negative 14, and that occurred at negative 4, negative 1. Okay, so our max and min there. Excellent. So if it's bounded region, guaranteed to have a min and a max. All right, now we got a different min and max we're going to check for into this objective function, y plus 2x. And I have these constraints already graphed. We won't take the time to do those again, but x is greater than or equal to 0, y greater than or equal to 0, 2y plus 3x is greater than or equal to 8. Just so you know, that one right there, 2y plus 3x greater than or equal to 8, that's this line right here. Okay. And then the 3y plus x, if you wanted to practice again, is that one right there. Okay. So you notice that we have the vertices are labeled there, 0, 4. These are the ones we're going to check. And then this is an unbounded region. You see how it just kind of keeps going out. There's no boundary to that there. So we need to be careful when we state our min or max. Do we have a min or max? And so on. So we check each of these first, and then we'll discuss the other here. All right, so let's check 0, 4. C equals y plus 2x. 4 plus 2 times 0. C equals 4. Let's plug this one in. Y plus 2x. C equals 5. Plug this one in. Y plus 2x. C equals 10. Okay, so if I'm looking at this right now, it appears, I'm like, well, it looks like that 4 looks to be my minimum value there. My minimum value. Could I have any other within this region a smaller minimum value? You know, if I'm plugging in any point that's in this feasible region, like let's say 0, 5, I say no, 0, 5 would be even bigger, 0, 6, and so on. Because you're thinking about this y plus 2x. So you want to minimize both of those. But again, it has to be in the feasible region. And you say, well, I want that definitely to be 0. I can't have any negative values that's not in my feasible region to have x values that are negative. So that doesn't help me. And my y value, the smallest y value that I can have really is that 4. Okay, so I'm definitely have this minimum right there. Okay. Now let's talk about the maximum. It appears our maximum is 10, right? C equals y plus 2x. But if you think about this region, feasible region, I can get a bigger y value. Remember, I'm adding the y and the 2x. I can get a bigger x value, like for instance, if I throw in 60, okay, that's still in my feasible region. And guess what? 60 gives me a larger c value. I can get even bigger. I go 70, 80. So I can keep getting bigger and bigger and bigger, picking points within my feasible region. So I really have no max here. Okay, remember the unbounded ones. you have to be careful with. You may or may not have a max or a min, okay? All right, make sure you guys bring your, we'll see you soon. Bring your questions to class. Thanks.